This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. This episode of SE Radio is brought to you by Braintree. If you think that your payment system exists solely for the purpose of transferring money from your customer's wallet to yours, think again. Braintree. Rethink payments. Learn more at braintreepayments.com/SE Radio.
For Software Engineering Radio, this is Jeff Meyerson. Morgan Wilde is an iOS developer at Shoplandia. He is the creator of a YouTube video called A Brief Introduction to LLVM, which I found to be a very helpful resource. Morgan, welcome to Software Engineering Radio.
Hey there, Jeff. Nice to be here.
So today we're going to talk about the LLVM, and I want to have a general introductory discussion of some compiler stuff first, before we get into what LLVM is, because it's related to compilers. For people who are needing a refresher, what are the high-level steps that a piece of code goes through when it gets compiled down to binary ones and zeros?
In a general sense, any kind of programming language has to end up looking like machine code that a CPU can execute. And obviously there's a whole bunch of CPUs and there's a whole bunch of programming languages. And there has to be something in the middle there to translate, so to speak, or compile the source into what a CPU would understand. A big step up from what we had before compilers, which was assembly language, which essentially was human-readable binary code. We would just issue instructions, and they were non-portable instructions. So if you say worked on Intel, you can do ARM or vice versa. And the compiler sort of created this abstraction layer over the machine language or CPU instructions by allowing us to program in sort of more abstract programming languages where we worry about the logic, sort of the things that we want to see happen, rather than thinking about what to instruct the computer to get to that point. And so any kind of source that you write in a language that is compiled, because there's languages like Python and PHP and Ruby that they're not compiled, they're interpreted live.
Right.
So any kind of compiled language does have a necessity of having a compiler to translate that into machine language.
Right.
So the first step is you take the source file and you basically just put everything into tokens. You just do like a syntax check, whether the tokens check out and whether it's a legitimate piece of language. And you compile trees into trees from that, and you get essentially a abstract, non-readable format of your code that just scrapes all of your your comments, your variable names, and all that stuff. And then depending on your architecture, from that abstract form, sort of cleaned up form, there can either be a direct translation into one architecture or another. The term here is target. So any kind of CPU architecture you're looking for is essentially a target. And so if you're targeting an iPhone, you have to worry about instructions that are different when you would be targeting a MacBook, for example. And so if you're directly compiling, like GCC, which is the GNU compiler collection, takes your C, for example, and just spits out machine code. Structures like LLVM create an intermediate representation of that code,
right? And
it can optimize that code and do all kinds of smart stuff that allows it to speed up your existing code. If you compile it, say 3 years ago, you would compile it now, and sort of you get the speed up, and that finally gets translated into machine readable code.
Absolutely. So let's talk about the pre-LLVM world before we get into LLVM. You touched on this idea of the N by N language to processor problem, where if, in a world without LLVM, you potentially can have this scenario where for each language and for each processor, you need an individual way of getting that language into a form that processor can understand. Is that accurate?
Yeah, it is a very big problem from, I guess, a few decades back that prevented and stagnated the industry, in that portability was pretty much non-existent before Unix came along and sort of created the POSIX standard. And sort of before that, before POSIX, you had people building all these architectures, and they didn't share a whole lot in common. And if you as a programmer required a simple task as reading from disk, you would have to abstract that part away yourself and take care of any number of architectures, because Unix does file reads one way. There's one command. Windows does it differently, and some architecture X would do it differently. So these things sort of stagnated the industry to a point where Java, when it came out, was this massive savior for the whole market, in that programmers started sort of dreaming about the build once and run everywhere mantra, which is pretty powerful when you're stuck in the world where you're limited in that regard.
Now, we're going to get into LLVM in a sec, but you mentioned Java and you mentioned a degree of portability that Java added. Can you explain what that portability was and what were some of the results of people being inspired by the Jvm model?
Right. Well, Java is sort of this poster child of that build once, run anywhere movement that sort of later was transformed into the web architecture, or at least inspired the web architecture, where pretty much you have this experience where you develop a website or a web service, and you have the expectation of being able to run those apps anywhere. So that came from Java, and JavaScript was sort of directly influenced by Java. And so what Java does is it takes your source and LLVM and Java has this part in common, where LLVM has the IR, or the intermediate representation, and Java has the bytecode. But from that point on, they act differently upon those two things, because what Java does is it distributes the bytecode, and you run it, you execute the last part of what a compiler would do, which is translate bytecode into machine executable commands runtime. So there is an inherent lag in any kind of Java program where there's like a 2-second thing that needs to happen for the bytecode to be loaded onto what's required for that architecture. And that simple fact of being able to carry that abstract form of your code in the form of bytecode, and then compile it only when you run it, certainly does have its benefit.
Right. So I think what you're getting at with this is that in the JVM ecosystem, you've got this bytecode, and the bytecode is this representation that's not super low level, it's not super high level, it's somewhere in between, and because we have this bytecode representation, we can move it between different architectures, and we can have the same predictable runtime experience on each of those hardware architectures. And LLVM borrows from this in some ways because of this intermediate representation that we're going to get to. But let's start simply. What is the LLVM?
Well, it's back in the day when it was first formed, it was a step towards emulating the bytecode sort of intermediate language between executable code and source code. And it turned into this pretty massive effort that's open source, and it's a whole ecosystem of compilers and their tools. And the thing that joins them together, the thing that all of them share, is the intermediate representation, or IR. And obviously the man, or one of the two men that created LLVM, is Chris Latner. He later joined Apple specifically on that achievement. It was, a graduate project. Most of us would dream of a graduate project that's successful. And it turned into something that I've heard recently. It's able to do C faster than GCC is able to do. So they started off a lot slower than C, but their whole mission is to create a optimizer for their custom intermediate representation that is able to continually optimize the code to the point where, it just gets better and better and better.
Yeah, so we'll get into as much of the LLVM as we can, but this is, for listeners who don't know, this is a really big subject. And basically, before LLVM, compilers tended to have this monolithic structure. And as you talk about in your YouTube video, which I'll have in the show notes, LLVM breaks the monolithic compiler structure into a series of steps. It breaks this structure into scanning, parsing, intermediate representation, the intermediate representation optimizer, semantic analysis, target code, and finally compiled code. And we could get into any number of these steps in the compilation structure, but as you said, the intermediate representation is really the area that we should focus on. So what is meant by that intermediate representation? What does an intermediate representation mean, and how do we get there?
Sure. Before that, I do want to clarify that.
Oh, sure.
You've mentioned 7 steps here. They're not unique to LLVM. And in general, when you're thinking about compilers, pretty much all of them have the sequence of those 6 or 7 steps. And so I want to stress that that's not unique. LLVM did not invent that sequence. What it did is it decoupled the IR from essentially what is the front end, meaning parts of the compiler sequence that are concerned with specific source code, source files, and the back end, which essentially is concerned with optimizing specific targets and then creating executables for those targets. So the key unique thing that it did was it sort of separated IR from the sequence here. Pretty much every compiler has that sequence, and pretty much every compiler has that sequence in a sort of modular-ish way within their own world. Yeah, I feel like none of them, at least not the big ones, they don't have the intermediate language as separate as LLVM has.
Okay, well, thanks for that clarification.
Just want to yeah. Because any computer scientist that goes to the compiler class, you'll sort of see the sequence, and it's there. It's not an invention that we can credit Chris Latner with. But
okay,
yeah. So to your question, IR is, well, it depends. Every system has its own IR, and it's just a step that eases the optimization steps, which create the executables that are speedy and performant. So what you have in regular source code, as I mentioned in the beginning here, is sort of high level structures. Let's take Swift, for example, because that's my favorite language. You have your classes, you have your structures, you have functions and methods and all kinds of high level stuff. Now, no processor operates on that level, and obviously they don't understand that. So in between machine code, executable code, and source code, you have this assembly-like intermediate representation. And when I say assembly-like, a lot of the people that deal with assembly languages can pretty much immediately feel accustomed to what's going on in specifically LLVM IR, because what you do there is, well, first of all, you don't work with variables, you work with registers. And to that point, the sort of the biggest difference from any kind of assembly language is registers are mutable. And by that I mean, let me see, when you have your RX register, you just put stuff into it, or you take stuff out of it, you read from it, and it's constantly changing state, right? It's a sort of a physical register that just constantly is mutating, and any number of parts within your code can change that. And being able to optimize any kind of dynamic data is a lot harder than optimizing something that's immutable. And so IR for LLVM has immutable registers, which is essentially just an unlimited sequence of let or const declarations that you do.
Okay, so let's go through a simple example. So let's say we had a program that we wrote in Swift. As you said, this is one of the favorite programming languages of today, of 2017. I think there was a Stack Overflow survey recently that said this was the favorite language of programmers on Stack Overflow. This is a language that is used to develop most iOS apps these days. So let's say we wrote a Swift app that was just x equals 5, y equals 2, and z equals x plus y.
Sum.
Yeah, and then like print the sum or something. So if we wanted to say, look, let's compile that and run it, maybe you can explain what happens to get to the intermediate representation point, and then what's going to happen with those registers in the intermediate representation and optimization step.
Right. So first of all, when you're tokenizing your source, say that x equals something, y equals something, Swift does a beautiful thing, which is called type inference. So you don't need to write int or float or whatever, but that step is required for the compiler to allocate the correct number of bytes and sort of be able to deal with the underlying data. And so what the first few steps do is they position everything that you've declared into sort of stack frames. And a stack frame is just concerned what tokens are you able to access within that stack frame, and what tokens will you be able to access from children stack frames. At that point, what you do is you get the token identifier, which is X or Y or Z, and then you get the type, and then you get the current value for that thing. And something as simple as sum, and this is one of those points that I showed in the presentation, is you take those types and you convert them into IR types. And obviously you don't have structures or classes, but you have pretty advanced types like function pointers and all kinds of numeral types and functions and all of that stuff, which is definitely a lot higher than what you would get with assembly like languages. And every single declaration of a register has to be sort of preceded by a type. So there's no type inference. You got your X and your Y, and they can be translated into anything, but all of them, all those identifiers will start with a % sign, and let's say %1, %2 would be your X and Y, and they would probably have an integer type. So let's say integer 64, depending on the architecture, of course, or 32. And like with any register, you'd be able to issue the add command. And the only difference is in terms of commands here, since your registers are immutable, so it's very much like a functional language, any kind of result from an operation that mutates data or potentially would mutate data is just a return value. So when you add stuff in assembly-like languages, you do like ADD and then one register and another register. You won't be able to do that here. You would have to, assign that value to another register, to a new register. And that's addition. And like the only difference here would be you take the plus sign, you turn that into ADD, you add the type identifier and your sort of values, and it's not too big of a deal when it comes to simple math.
So it sounds like there's not much optimization going on in this example. Is that right?
There's zero optimization.
Okay. So what kind of things will we need to add to this code in order to illustrate the optimizer?
Well, let's say y would be 0. So your x is 2, your y is 0, and you're adding these two numbers, and you're using the sum. And if you're defining the value with just a numeral, you could optimize that out yourself. But oftentimes when value is defined in like a static let somewhere in a struct that is far away, you don't see the value, and these things easily happen. It's one of the most popular optimizations here. And what a processor would do is you'd waste a couple of instructions at least to do that non-operation essentially, because adding 0 to anything does not change the value. So to save those couple of instructions, a couple of cycles, IR looks for common patterns, and the sequence of patterns is constantly updated, and it can it's a growing list, and it obviously differs by the types that you're dealing with. So say any kind of numeral type would have plus 0 equals the same value. You can optimize that out. Times 1, the same value. You can optimize that out. And all that mathy stuff you can optimize out. And the way it works is deep in the C++ that's dedicated for LLVM, there is a split, a branch, depending on what kind of operation you're doing, that takes you to a for loop that iterates through all the possible optimizations for a specific, I forget what the sequence is called, but for a specific sequence of code, which is essentially any kind of operation. That add would be one example, move would be another example, and and so it loops through all the possible options there, and it applies the optimization for and assigns the result to a temporary variable, and then it checks whether, first of all, whether there's no errors that are introduced by that change, and whether there's any value gained from that operation. And then if that's true, that gets substituted into the original code.
So you're saying that when I compile my Swift code, after it gets translated into the intermediate representation, there is a tree of possibilities that are created to attempt to see, is there a way to represent this same code in a more concise fashion than the original naive intermediate representation that we've created? Is that right?
Yeah, well, first of all, you personally, you should probably never deal with IR directly, and so the first step is sort of the naive translation verbatim of what you see in your source file into IR, and then essentially only then can you do the optimization, because then you're dealing with immutable registers and a structure that inherently is more accessible to scans like that.
This podcast is supported by Atlantic.net, hosting solution provider of healthcare HIPAA, PCI compliance, and ad tech. If you're feeling the pain of having outdated technology, call Atlantic.net and get the latest security firewall, intrusion detection, backup, disaster recovery, and virtualization. Or if you're starting a new project or not getting the results you want from your current providers, Atlantic.net can help you succeed. With fully audited solutions and 23 years in business, they won't let you down. Visit Atlantic.net to learn more.
So if we're looking at all these different potential configurations of our code, that sounds like something that would be really, really time intensive, especially for complex programs.
Well, if you remember when Swift came out, the compile times for something that was bigger than a few view controllers, they were pretty big. And you're right, it does take time to optimize the optimizer for a specific front end. But the main thing here is that any kind of performance gains from, say, someone working on optimizing C, and obviously to optimize C, you have to go through LLVM IR and do some clever optimizations over there. And guess what? Those same optimizations translate to any front end that gets compiled down to IR. So people that are working on these, I don't know what's the number of languages that have front ends to LLVM IR, but it's pretty big. And some of the languages are very well used. Those optimizations get shared.
Right. So I want to eventually get to the modular part, but a little more on this intermediate representation optimization stuff. So I am reminded of the Deep Blue, the IBM Deep Blue stuff, because this was the chess computer where, given any chess scenario, Deep Blue would look at all of the potential decision spaces that you could potentially go down and play out the entire chess game down that part of the decision tree. And it sounds like the intermediate representation optimization is like that level of complexity, because if you're looking at the entire tree of possibilities for different ways that your code could be arranged, that to me, in a complex program, that sounds like it is just too much work. Is that accurate, or is it possible to break down?
I wouldn't say in a way it is, just in that you end up looping over the entire sequence of a specific optimization, but you're not looping for every existing optimization for each line of code or each operation, because an operation is the atomic unit there. You're looking, first of all, what you're doing is you're putting that existing operation and the existing variables into a specific slot, a niche. And that alone reduces your problem space significantly. And obviously, when you reduce your problem space, you're not dealing with what's the chessboard total probable when you start a game.
Right.
Trillions? I don't know what that is.
I don't know.
Yeah, so you're not dealing with anything of that scale, because you have this inherent step of you take an operation, and then you take an existing the existing identifiers, the values there, and then you only go through the appropriate optimizations for that. And there's obviously predictive stuff going on there, which I'm not in depth on, but from what I know, it is certainly not enumerating everything that you can possibly think of.
And this certainly sounds like a problem that could be assigned across multiple threads, because if you're testing these different...
Oh, these are super parallel. Like,
yeah.
when you're dealing with optimizations here, you're optimizing each individual operation. You're not optimizing in terms of multi-operational sequences. So the parallel nature of this whole thing is very great. Yeah, absolutely.
When you say operation, maybe this is a naive question, but what do you mean? What is an operation?
For example, add one register to another.
Okay. And can you explain some other examples of operation? Because I guess I'm having trouble understanding where, like add one variable to another. That doesn't sound like something where there would be that many different configurations to test. Maybe you can help me to clarify.
Oh, I mean, there can be, a whole bunch of them. Obviously, you have your load and store, you have your control transfer ops, you have your type conversion ops. Like when you're adding, obviously in Swift.
So you're illustrating add as a fairly high level operation that gets translated into a bunch of low level operations.
No. Add is as low as it gets.
Okay.
Yeah. There's nothing that...
Oh, I see. You're talking about other operations.
Other sort of equivalent, parallel
right.
operations, yeah.
Right, so load and store. Maybe explain what a load and store operation is.
Well, loading is reading from a register, and storing is writing to a register.
Okay, and that's an example of something that you could see being optimized if it was tested in different...
Yeah, well, say you're reading a value and assigning that to another value without any kind of mutation. An optimization would be anywhere you're using the variable that the identifier that you're assigning to, you could just replace with the identifier that you will be assigning it. So if it's a constant, obviously if it's a variable that can mutate the underlying value, you can't do that. But if it's a constant and you're assigning just that, basically creating an alias, you can optimize that out.
Okay, so you're giving an example where, you take a load and store operation and you test different ways of doing it. You might get memory savings, you might get time savings based on variable reuse, for example.
Yeah, well, any kind of variable that you don't have to assign is a variable that you don't have to get space from your stack for, is a variable that you don't have to deallocate the memory for, and it's always a plus to having fewer.
Cool. Okay, so before we hop out of the super lower level stuff and talk about some of the flashier characteristics, so we talked about this load and store, just to close the loop for some people who may not like load and store. That doesn't sound like anything I use in my programs.
Absolutely not.
Can you just illustrate what would be a higher level line of code that might end up translating to a load and store operation?
Assigning a variable from another variable would be an example of a load and store, because any kind of assignment, it's a single operation in like Swift. You just do A equals B, but there's an abstracted command even in assembly called move, which essentially does two things. You can use move from memory to memory. So like anything that's on the stack, you can move things from the stack or within the stack. And if you're dealing with registers, there are certain instances where you would have to sort of read from a register, put that into memory, then take that memory and read it into and write it into another register where you can't do a flip. So you would need to load and store that type of thing. But this is something a programmer would never interact with in their daily life, because thank God these things are abstracted away, and all we deal with is view controllers and transitions and all that beautiful stuff.
Okay. Yeah. So you've given us a beautiful, I think, from the top to intermediate representation explanation, and I think your earlier conversation sort of gave people a picture of what happens after the intermediate representation. It goes down to machine code, and there's some processor stuff that happens. If people want to know more about that, they can look into how compilers work, or basically what happens after the intermediate representation. But I want to talk more about why this intermediate representation is a big deal, because essentially, if you can get any piece of code into the intermediate representation can do a lot of optimizer work, and we can have a open source collective working on the intermediate representation and driving gains for any of these other languages that can compile down into the intermediate representation. So we're talking about Swift and Rust and anything else. So maybe you could talk about what are the challenges that a language has to overcome in order to be able to convert into this intermediate representation.
Well, that's a little sort of beyond what I can contribute.
Okay.
It's a topic that I know a lot of people go through when they think about, doing like a hobby project of a sort of language, and most of them pick LLVM as a way to compile it into executable code when, toy languages. But
fascinating.
Yeah, it's from what I heard, it's one of the easier, or probably the easiest, or maybe even the only viable option there when you're creating a new language, whether the audience would be just you or even if it's bigger.
So maybe 8 years ago, people might have said, I want to write a new language, and they write Scala, and then they say, okay, I want this language to compile down to a machine, so I'm going to write it for the JVM, or I'm going to write it to compile down to bytecode.
Most likely what they would do is translate that into C, and then just use GCC, their compilers, to get to machine code. And so I think Haskell has this attribute where their functional programming source gets translated into C, super unsafe C, and that gets transferred onto machine code.
So you're saying that in the past, people might have used C as the interoperability layer,
yeah,
whereas today we can do LLVM.
Well, and so it's very important to say that GCC is like the big dog here, and I think it still is, since it's been going for, 50 years now, 40. Who knows? It's a super massive project, and inherently it has a lot of optimizations, whether they're good or bad, whether they're modular or not. You can produce super quick executables with GCC, and all you need, like when you think about intermediate languages, you think low level sort of memory access, CPU instruction access, and you get a lot of that with C. Tweak it a little bit, and you can get to raw memory. A lot of these embedded systems use C as their sort of interface language, and C inherently has a lot of properties that IR has, and so it was sort of a natural use for the language until something came out that had the sole purpose of being in the middle. So C does still take up that a little bit. But obviously it's being phased out, but by tools that were made specifically for that task.
Well, safety is something that I have heard. You're not the first person who I've heard mention like C is somewhat unsafe if you want to build a systems level language, and Rust is something that I've heard is a language that has some safer properties than C, and perhaps some of that is due to being able to be built on top of the LLVM, on top of the intermediate representation. Is there some notion of safety that is built into the intermediate representation?
No, because when you think about safety, you don't think about the language itself most often. What you think about is things that people build with the language. So you have a human component there to abuse safety and turn it into something that's unsafe. For example, a lot of people are taught C, and when they go through sort of the initial tutorials, they see how to read and write data from the terminal. And obviously that's been outdated for God knows how many years, and it's no longer safe to do it that way. So when it comes to safety, either you're using a framework that someone wrote that's not a systems engineer or a compiler designer, and it's unsafe because it's using some part of the language unwisely, or you're responsible for your own code and you don't know something, or you have a leak, or you don't check input or something like that, and you create unsafe sort of programs. But the intermediate representation does not in and of itself create safety issues, because the loop is pretty much closed there. And you have that with higher level stuff.
Okay, so I jumped the gun on talking about Rust. What is Rust able to leverage from the LLVM?
Well, that's as far as I know in terms of Rust. It's using the backend for, the source is created by the open source community, and they worry about the definitions there, and how to organize the language. But the part that is the most difficult and optimizing what that would require the most resources is the back end, or how to make code run quickly on Intel, on other architectures other than x86. And that's where you get the built-in benefits from LLVM by using their backends for, I think they have backends for pretty much every single platform that's big. Definitely ARM and x86, and so that pretty much allows you to reach that whole market. So if you're developing any hobby language, and I mean Rust is still at a point where, in most cases, I might be ignorant to any kind of big existing project that uses Rust as their main language, but I haven't heard of any at this point. And so
Dropbox.
Really?
Yeah.
I heard they're Python driven mostly.
I think the Dropbox. I think Dropbox is Rust now. Anyway, I'm sorry to interrupt you, but yeah, I'm pretty sure that they moved off of the cloud recently, and when they moved off the cloud, they rewrote a lot of stuff, and I think that they used Rust. But anyway, I'm sorry to interrupt.
Well, there's probably parts, any kind of startup.
Yeah.
Even individual developers have tools that they write. I think I deal with 5 different languages on a daily basis, pretty much.
Fair enough.
And that's just because you use different tools for different purposes. And so regardless of that fact, it's still a very nascent language.
Yes.
And
yes.
You either dedicate your resources, and that's probably the whole point of having these beautiful projects like LLVM, is that people can now work on things that they're the best at, or at least try to be the best at one specific part. And so with LLVM, Rust people don't have to worry about being good Intel architecture people, or ARM architecture people. They just need to worry about how to deal with memory and how to deal with a good structure, and sort of focus just on the front end. But that's a big picture commentary. I wouldn't be able to do more than that.
We talked about JVM versus the intermediate representation layer a bit, and Java Virtual Machine. LLVM stands for Low Level Virtual Machine. Probably should have mentioned that earlier.
No, it doesn't stand for that anymore.
Oh, that's right. It used to. Oh yeah, now it's just LLVM.
It's like BMW is BMW. You don't enumerate what each letter means.
Well, so anyway, where I was going with that was that there is an analogy to be drawn, because in the Java bytecode ecosystem, you have this shared layer, the Jvm Bytecode Layer, where people will write, people will have a big Ruby on Rails application. When they hit a performance bottleneck, they will switch to JRuby, which is a version of Ruby that runs on the Java virtual machine. Basically, as I understand, JRuby is Java, so you can compile Ruby to JRuby, and then JRuby runs on the JVM, the Java bytecode, so it runs faster. You get to take advantage of those bytecode optimizations. And similarly, we've got this intermediate representation that we've been talking about, where Rust can compile down to it, Swift can compile down to it, and we have these optimizations that are shared on a platform. And how does the Java bytecode ecosystem compare to the LLVM intermediate representation ecosystem today? How would somebody choose between writing their language to compile to Java bytecode versus compiling to intermediate representation?
Well, to some extent, they are different animals, and you can't do like an apples to apples comparison because they take up different niches, I think. IR is substantially lower level than what you would get with bytecode, meaning even though IR is isomorphic in that you can translate it to Bytecode, which is like a super tight version of what those operations and commands look like, to human readable IR and memory stored IR. But human readable IR is not source code that a person would be able to tell, just skimming through it, what the program does. Whereas JVM bytecode, you can actually take it and it's isomorphic to the source level. So what you have is, even though you lose the original identifiers, and that can take away some part of the meaning, or in some instances a lot of the meaning, but you still have a line for line representation of what the source code looked like. So that is probably the major difference there. And you can, by the way, you can check that difference by just inquiring into. I know this for a fact. You can do that on Android Studio, so any kind of IntelliJ IDEs, where you can open up libraries that are compiled into bytecode, and you can look through the actual Java code without the identifier names and all of that, but you can still look through it, whereas IR does not have that quality.
I want to begin to close off and just talk about where the LLVM ecosystem is at today. As you mentioned, LLVM was originally just called the low-level virtual machine. That's what it stood for. Now today it's called LLVM. It's literally just called that because it's representing a larger ecosystem of compiler tools. Can you explain?
Specifically, the biggest parts would probably be the linker, LLD, and LLDB, which is the debugger. If you've worked on Xcode at all, you would see LLDB messages pretty often. So when you add breakpoints and stuff, that's when you're dealing directly with another piece of the LLVM architecture. That's the debugger. So those three parts are probably the biggest. I mean, if you abstract away IR.
Now, is that debugger, I guess that's running, so what happens is you compile your code, it goes through the intermediate representation, it gets optimized, and then it runs, and then you are debugging against the intermediate representation that was settled on after the optimization. Is that right?
Well, you're debugging against live code, but that code is obviously annotated so that you can have access to the code that you wrote in Swift, for example.
Right, okay.
It's not like a stripped down version. So any kind of debugger adds a layer to the intermediate executable code that can, transfer some data. Because and so when you exhaust that, you oftentimes are taken to IR or some form of IR, and then you just see a whole sequence of registers within a specific stack frame, and then God help you finding what went wrong there. So the LLDB debugger takes care of that specific part. But yeah, it's in the Apple ecosystem. You probably don't veer too far from the entire sequence there, because you're linking your stuff with the LLVM linker against your static dynamic libraries, and you're debugging with your debugger. So yeah, Xcode is very much reliant on LLVM.
Okay, so I want to wrap up with one. I want to make one quick point, I guess, that people who are maybe new to thinking about compilers, the reason we're spending so much time talking about this optimization stuff and why this is so important is because if you can spend a lot of time automatically optimizing your code, then every end user who is executing that code gets to take advantage of the optimization. So even though the developer who is compiling the code might have to wait around while the different intermediate representations are being tried, once it settles on an optimal one, all of the end users who are actually executing that code get to take advantage of the optimizations. So, but with that in mind, is that the main thing that the ecosystem is focused on? So when we're looking at the future of the LLVM and the things that are going to develop out of this ecosystem, what should we expect? Should we just expect more optimizations that are going to be made on the intermediate representation level, or better debugging tools, or is there something bigger that is being worked towards?
I'm pretty sure what you've just mentioned would be a good characterization for it. Essentially, what LLVM allows you in the future, I guess, you can probably see more new, exciting, different languages being created because you don't have the inherent bottleneck of worrying about sort of how that thing works on the different systems. So that's one possible outcome. You'll have a lot of front ends sharing their optimizations between each other. That's a big boon for the industry because, those resources are very valuable. So whenever you can share or collaborate with other people, that is a great benefit. And yeah, I mean, it's going to be interesting to see what happens with the collection of tools here when Chris is no longer with Apple and no longer working actively on maintaining, as he was the primary person there since he moved to Tesla. So it's going to be interesting how they're going to deal with the future related stuff come WWDC this summer.
Okay, Morgan. Well, is there any social media plugs that you'd like to give for people who would want to follow you? What are the best ways to follow you?
Yeah, I use Twitter, and you can find me Wilde at Wilde Morgan, last name, first name, on Twitter.
All right. Well, Morgan, thanks for this illuminating discussion of LLVM. I think you gave a really clear explanation. I liked that we were able to dive deep and go higher level, and I recommend anybody who's looking for further information on this to check out your YouTube video, which is only about 30 minutes long. That's why I liked it so much, is that it was concise and yet deeply informative. So thanks for producing that.
Yeah, it was a love child, I have to say. It took probably 3 weeks to get the thing together. It's 20 minutes, so yeah, you can have a pretty good refresher on not only LLVM, but the whole ecosystem for compilers.
All right. Morgan, well, thank you.
Thanks for having me, Jeff. It's been a pleasure.
Help us make SE Radio even better by completing our short listener survey at www.ieee.org/SE Radio. Thanks. Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.